Hey gang, Mr. Helly here. Hope you guys are doing all right and enjoying your kind of serendipitous time off. Um, Today, really what I have for you, and hopefully it doesn't take a tremendous amount of time, is that we're going to talk about polarity and the cell membrane. I don't really feel like I can talk effectively about the cell membrane without talking about the concept of polarity. And this is more of a chemistry concept than anything, but it's a huge concept um, to to a lot of things biological, because polarity will sometimes either prevent or allow things to get across the membrane. Now, what is the membrane? Okay, so we drew this the other day when we did our we were talking about the chemical synapse, right? Well, this line right here that goes all the way around on both things, that represents the membrane. And the membrane is the barrier between the cell and the outside world. It's how a cell can manage and regulate what goes in, what stays out, things like that. This layer is so crucial to all life, and all living things have that. Okay, but before I get into any great detail on the membrane, we've got to talk about polarity first. So, what does that mean? Polarity essentially equals charge. Okay? Um, so, if something is polar, it has a charge, either positive or negative. And it doesn't have to be completely charged like an ion. Sometimes it can just be partially charged. Where if something is nonpolar, has no charge. And it's not like an all or nothing thing. There's a range between nonpolar and polar, so you can kind of fall somewhere on this range here. There are things that are completely nonpolar, and there are things that are highly charged, and there's everything kind of in between the two. So what is this charge the result of? Well, it can be either having um, an extra electron, or a lack of an electron, like sodium is charged, and A plus is charged because it has lost an electron, because it missed an electron. Cl minus is charged because it has gained an electron, and so there's a full charge. But there's another thing called is partial charge. And this is most of the situation when dealing with molecules. Partial charge is the result of unequal sharing of electrons. You see, we talk about how electrons are shared, for example, in covalent bonds with water, for example. So here we have oxygen and a couple of hydrogens, and they're going to share electrons. Oxygen is going to benefit from the extra electron in the orbital here, and hydrogen is going to benefit from the electron in that valence of oxygen there. But the trouble is, like, not all sharing is equal. Okay? Not all sharing is equal. What happens is this: some atoms have a stronger pull on electrons than others. Oxygen is extremely electronegative. Like, in a perfect world, this is what it would look like. The electrons would kind of float between orbitals like this, it'd be like, okay, hey, cool, we're sharing equal time. But in reality, this is what happens. Because oxygen has such a strong pull on those electrons, they're going to pretty much spend most of their time orbiting that oxygen atom, and then occasionally zip out there to orbit that hydrogen there. Orbit, like that. As a result, because those electrons are negative, and the same thing's happening over here too at the same time, it's going to result in what's called a partial charge. And we're going to use the lowercase letter gamma, which looks like that, kind of like a fish that's diving down, for partial charge. Partial charge is like that gamma. So this right here is going to be partially negative because electrons are negatively charged, okay? And because the electrons are hanging more around oxygen than around hydrogen, then you're going to end up with, sorry guys, my camera is wiggling here, I have it kind of rigged up, because electrons are negative, it's going to create a partial negative charge here because they're constantly wanting to fly around or orbit around oxygen. As a result, hydrogen is going to have a partially positive charge because it's spending less time with that electron. So anytime there is unequal sharing of electrons, okay, if there's unequal sharing of electrons, that means that thing is going to be polar. Water is polar because the electrons are not shared fairly or equally. So the question is, how can electrons be shared fairly or nonpolar? Well, the only way you're going to get them to share it equally is one of two things. One, they're the same element. For example, when oxygen shares with oxygen, oxygen has the same electronegativity as oxygen because, well, shoot, they're both oxygen. So that electron is going to fly around each of those equally. And as such, there is no partial charge. So this is nonpolar. And that's the same for when nitrogen shares with nitrogen or hydrogen shares with hydrogen. Anytime you have the same element sharing that's formed a covalent bond like that, you're going to end up with it being nonpolar. And then the only other way is with different elements with the same electronegativity or same pull on electrons, okay? And there are a number of different examples, but here's the ones that matter. You ready? Carbon and hydrogen. These two, I know they're vastly different. Hydrogen has only got one atom, and carbon, or one proton, and carbon has 6, and there's different numbers of orbitals and all these other things. But here's what happens. Because of the way that the electrons are distributed within carbon and the way that the protons and neutrons are distributed, it displays the exact same electronegativity as hydrogen, which means that if you get carbon and hydrogen to bond together in any way, when there's no other things that are bonded to it, the electrons get shared fairly in all directions. So anytime you have this right here, which is considered a hydrocarbon, there is going to be an equal sharing of electrons between carbon and hydrogen, and it is non-polar because there will not be any stronger attraction of electrons between carbon or hydrogen, so they're fairly and equally balanced. What you need to know about nonpolar things, and you probably already do, because hydrocarbons include things, for the most part, and this is a little bit simplified, but like oils, waxes, gasoline, paint thinner, okay? Those things are all hydrocarbon based. And when they're hydrocarbon based, you can't wash them off with water. If you've ever got like Crisco on your hands and you try to wash it off with water, you'd be trying to wash it off forever and it doesn't seem like it would come off. That's because it doesn't mix with water, because water is polar and hydrocarbons are non-polar. You're like, well, what does that have to do with this cell membrane? You know, why are we taking this chemistry jaunt? Okay, because we have to talk about this guy, okay? And let me do this. Take a little corner right here, and I'm gonna talk about this cat right here. draw that circle with a couple of squiggles like that. This is called a phospholipid. A phospholipid. Now, oils, waxes, I put the word fats in here too. Oils, waxes, fats, things like that. This is, look, two words here. We got phospho on one side and lipid on the other, okay? Up here is the phosphate at the top, and it is polar, okay? You're like, what is this thing? Why did we just shift over to this? What we've just drawn here is a simplified drawing of the most prevalent thing you're going to find in the cell membrane. A phospholipid is like the key ingredient to the whole thing. Like that, this makes up a majority of the cell membranes of every living thing. Okay, so the phosphate is polar, and then down here are non-polar hydrocarbon tails. Okay, so the heads of these things, phosphate, the head is polar, and the tails are non-polar. If you took a look at one of these and we were to zoom in on it, here's what you would see. Carbon stuck to carbon, stuck to carbon, and hydrogen slapped on every which way. Now, occasionally you'll see a spot where there may be like a bend in it, like I show you these little squiggles back and forth, where you see a bend like that. We would be light one hydrogen on each side, and that's and sometimes carbon will double bond like that, but that whole chain is made out of hydrocarbons. That's why it's non-polar and it repels water. Well, you know, most of living things are made of water, like inside and outside. They're pretty much all made of water. So how in the world does this work? It's a brilliant, brilliant system. So basically, these things will arrange themselves into what's called a phospholipid bilayer. So we're going to take these squiggles here, and I'm going to take one like this, okay? And what they do is they arrange themselves back to back like that. In this double layer. It's brilliant, okay? So let's say this is the outside of the cell, and this is the inside of the cell. Because their tails repel water, they will mix with each other and form this double layer. It's a fantastic way to do this. Now, it will bounce things that don't belong. So any polar molecule that tries to work its way in here will get bounced out by those non-polar tails, okay? And then, you know, anything else that's not supposed to go through will get bounced like that. But things that can get through very easily, one of them is O2. Because it's non-polar, it can cruise right through. So when you're getting oxygen, you're breathing stuff in and it's getting into your cells, it doesn't have to go through any gates in the cells. It just goes right through the membrane. Sorry, hold on. My apologies. I'm still kind of on the mend here. Okay. So that oxygen will get straight through. Similarly, now I know it seems like this one's breaking the rules. I screwed that up. That's not how that's drawn. Okay, CO2, not OC2. Because of these double bonded oxygens on either side, and because they're flanking this carbon, both sides of these would act as though it's non-polar. So carbon dioxide actually floats right through there as well without any trouble. So the majority of the barriers of all of the cells, by like 95% or more, are made of these things. It's called a phospholipid bilayer. phospholipid bilayer, and it kind of makes sense. It's double layer made of phospholipids. Well, that's great, but what about this guy? What if this molecule actually needed to get in? Okay, now we need to add some other things. So there are some specialized gates in here as well. So draw like these two weird bean looking things stuck in there. Okay, this right here is a membrane protein. Now they take a number of different forms, but channel or gate, these are specific to what they will allow into the cell. So let's say this one is a sodium gate. Its job is to allow for sodium ions to come into the cell. So they would come in through that gate, okay? And that gate can be closed or it can be opened based on things within the cell and what the cell decides to do. And sodium is just one example. There's some that are set up to allow water in, called aquaporons. There's some that allow potassium in or out. And there are some that allow, you know, gosh, so many different types of things to be able to be transported in or out of the cell. But these gates are super important because they're what allow the cell to make choices about what is good for the cell and what's bad for the cell. Okay, there's a few other little details I want to throw in here too. In between each of these little things right here, draw you a little squiggle there. They don't have to be between all of them. Just draw a couple blobs like that, somewhere in between. Those things are called cholesterol. I know cholesterol. Well, I'm just going to start over. Cholesterol. Cholesterol gets a bad rap. And I will tell you that some cholesterol is very bad for you. But you do need some cholesterol to be able to basically will make the membrane rigid. Remember how I said, you know, those tails are all squiggly? This is not like a brick wall. It's like it's called a plasma membrane because it's like weaving back and forth, okay? But these things stuck in there are kind of like wedges that make it a little less squishy and flexible and a little more rigid, a little more resistant to that flexibility. In addition, there may be, a lot of times there are, and then I'll show this one coming out of the back there somewhere, carbohydrates that will make these chains on the outside of the cell. Carbohydrates, which would sometimes combine with proteins to make something called glycoproteins, but these guys right here are carbohydrates. Carbohydrates on the outside of the cell. A lot of times these will serve alongside proteins as like receptors and things like that. And sometimes the carbohydrates are going to allow a cell to combine or stick to another cell. Carbohydrates can be sticky. If you've ever had a Jolly Rancher and you know it's been sitting in your backpack for a little bit and you try to peel it, you know, the plastic off, you know, sugar candies and things like that can get sticky because carbohydrates, you know, they allow a fair amount of stickiness, and this can allow a cell to stick to, there it goes again, sorry, stick to another cell too. So they can be receptors. They can allow them to adhere to other cells and things like that. So recap, these are phospholipids. Their tails are polar. Oh, sorry, their tails are non-polar. Their heads are polar. That keeps them from allowing polar molecules to come in. They get bounced. But non-polar molecules just cruise right on through there, no trouble. Then we have gates like this right here. This one was specific to sodium, but they can be specific to pretty much anything. any type of molecule that the cell would regularly need. And those membrane proteins serve as gates. And they're not always open. Most of the time, they're going to be closed, and then they'll open up when the cell allows them to open up, and then they'll close up when the cell wants them to close up. Then cholesterol in here is making that membrane rigid, so it's not quite so flexible. It's going to have a little less, bounce to it. And then carbohydrates can allow cells to stick together. It can also allow cells to receive messages or connect to or communicate with other cells. Okay, so that's really it. So this right here, what you're looking at, is a zoomed in of this line here and this line here. And if I don't give you, this isn't too much information, those little receptor proteins we drew on here, that was that guy right here. Okay, and we'll talk about how that works in greater detail as we get into action potential. Thank you guys for joining me on this session. Feel free to reach out, email if you have any questions, and have a great day.